Hi, for those who joined on YouTube, can you guys confirm if you can see my screen? Can you please confirm if you can see my screen and if you can hear me? Guys, I don't see your comments. Can you please confirm if you can see my screen? On YouTube, guys, please confirm. I don't see any comments. Can you see my screen? Can you hear me? I don't see any comments, guys. Please confirm if you can see my screen. Oh, okay, great. Let's start now. Let's start. I'm with the learner in the session. This is the paying students. I'm currently working with the learner. So please watch. I'll also read your comments, okay? I'll also read your comments. Emihle, hi. How are you?
Morning, sir. I'm good, and you?
I'm good. Thank you very much for joining. Today we're going to start with work, energy, and power, okay?
Yes.
Nice. So now, uh, let's start. We're going to discuss some of the things that you need to understand in order for you to do work, energy, and power. And remember, last time we talked about, uh, we did, what is this? Newton's law. So some of the things that you learned from Newton's law, we're going to apply them on this lesson, okay?
Okay, sir.
Yeah, nice. Okay, so I'm going to try by all means to move slow. Né? I'm not gonna move fast, but we're going to move slow. You understand?
Okay.
Let's start with work. What do you understand by the word work? What do you understand by the word work?
Energy being released.
Energy being released. So this tells you that on this session, we're going to talk about work done by a force. Né? So if work is done by a force, what will be the work done by a force? That will be the product of the displacement and the component of the force that is parallel to the displacement. You understand? So what we're going to say is that the formula that we're going to use, work will be equals to the force multiplied by delta x. Are you happy with that?
Yes.
Right, from this formula there are some of the things that I need you to remember. Remember that this W stands for what? Work. And what is the SI units for work? Work is measured in joules. And we're going to have this F here. This will be your force applied. Okay?
Yes.
So this will be your force applied, and the force applied, it is measured in newtons. And we have this guy here, the delta x, which is your displacement. I think you still remember these things, right?
Yeah.
And remember, displacement is measured in meters.
Yes.
Are you happy with that?
Yes, sir.
100%. So, listen, for work to be done by a force, the force must be parallel to the direction of the motion. That's very important. It's important for us to note this down, that in order for us to do work, for work to be done, what are we saying? We are saying that for work to be done by a force, that force must be parallel. We need to make sure that the force is parallel to what? To the direction
Of motion.
the direction of the motion. I hope this makes sense. Okay,
Okay.
nice. So work, if we talk about work, work is not a scalar. The work done, this is not a scalar. Why is work not a scalar? It's not a scalar, and also work is not a vector. Tell me what? Why is work not a scalar, and why is work not a vector?
Because the work that you do does not have a direction.
Very correct. The work that we do does not have a direction. The reason we are saying that work is not a scalar and it's not a vector is because the work, it does not have direction. Okay? Right. So now let's talk about positive and negative work. Now we're going to discuss what we call positive and negative work. What do you remember about positive and negative work?
I don't want to lie, say I don't know what's positive and negative work. But maybe, let me try to guess that positive work would be like that good kind of work.
Okay. So remember, if the force acts in the same direction as the motion, an object, the work done by the force is positive. That's what I wanted you to remember. Like we say, if the force, let's say I have a force, okay, and the force acts, let's say I have a force, and this force, it acts in the same direction. The force acts in the same direction as the motion. Of the object. What are we going to say about that? We're going to say the object, the work done by that force is positive. You understand that part? by the force is positive. So now you understand what will be negative work. Right, now you understand what will be negative work. So the force is going to be positive if the force is in the same direction.
Okay.
Right. So what I need you to remember is that
Yes.
only components of the force parallel to the direction of the motion do work. Please don't remember that. Don't forget that. I'm saying don't remember that. And I want you to remember that information.
Repeat, sir, please.
I'm saying that only components, remember it's here. For the work to be done, we said the force must be parallel to the direction of the motion. So, in order for the work, only components of the parallel to the direction of the motion are the one that will do the work. This is the statement that I'm talking about here.
Okay, they will do the work.
Yes. So let's assume that we have an object. This is my object, okay? Right. So on this object, let's say we have the force. This object can see that we have the F applied to that. We have a force applied to that object. So the force, can you see now we have the direction of the motion. I'm just going to indicate where is this object moving. We're just going to call it the direction of the motion. Okay, so now the direction of motion. So this thing is going in that direction. So can you see that the applied force and the object, so the force is applied in the direction of the motion. Can you see that? So the force is in the same direction as the motion. So what will this do? We're going to work done by the force is positive. Why? Because we're going to say the work done by the force is positive. I hope you are happy with that.
Yes, sir.
Why is it positive? Because the force is in the same direction as the motion. Is that making sense?
Yes.
Good. Now let's say I'm going to have an object like this, but this time let's say the force is applied at an angle, right? So remember, if the force is applied at an angle, we're going to have components. So what I am going to do in this one, let's indicate the direction of the motion. So for this one, I have the direction of motion is going that direction, and then look at where is the applied force going. The applied force is not going in the same direction, you understand?
Yes.
But what I need you to remember, is that these components will have a horizontal component pointing in that side. This is my Fx, and it will have my Fy going up. So this will be my Fy. I'm not sure if you still remember that.
Yes.
Okay. So what we're going to do, this is our F applied, and it's applied at an angle.
Yeah.
Are you sleeping?
No, sir, I'm not sleeping.
Okay. Right. Look at this. Only the horizontal component, only our Fx. In this problem, only Fx of the force, will do work.
Oh, because it's moving in the direction of motion.
Is thus work. You see?
Okay.
It's easy like that. So what we are trying to say is that the horizontal force It's in the same direction as the motion, so the work done by the horizontal force is positive. Therefore, we can conclude and say that work done by the horizontal force is positive. I think this makes sense now, because in order for you to do your calculations correct, you need to understand this concept. You see, once you are done with the session, you'll be happy to do past papers, okay? So now let's talk about if the force acts perpendicular to the direction of the motion. What will happen?
Isn't that going to be negative work?
Okay, remember, if the force is perpendicular, no work done. There will be no work done.
Oh, but then if it opposes it,
exactly.
Like it's in the opposite, it becomes negative work.
Exactly.
Oh, okay.
So what you are trying to say is that if I have a force that acts perpendicular, what can we say about that? Perpendicular to direction of the motion, we're going to say that no work done.
Okay.
By that force. Okay?
Yes.
Right. I think we discussed too much. So now what I need you to do, we already know that if the force goes in the same direction of the motion, the work done by that force is positive. So now, if I put a frictional force here on this object, let's put a force that is going that side. Can you see that the work done by let's call this Fk, the work done by Fk will be negative. Can you see that?
Yes.
Yes. The work done by that force will be negative. So, I think now you understand positive and negative work done, okay?
Yes, I get it now.
Right. Just give me a second. Okay, I'm sorry. Let's look at the alternative work done formula that you'll be given on the data sheet. So on the data sheet, they'll give you the formula that says work done is equal to the force applied multiplied by delta x, the cos of theta. Okay? I think already we know what is our F, we know what is our delta x, we know the angle. But now remember, the theta is the angle between what? Tell me, what is the theta?
What is the theta? It's the angle between between where, sir? I don't understand what sir's trying to say.
Okay, is the angle between the force. When we calculate the work done, the theta will be the angle between the force and the displacement.
Oh, okay.
Right. So now, when we use this formula, please note that when we use this formula, the angle will be the angle between the applied force and the direction of the displacement of the object. So if an object is on incline, the angle in this formula is going to be what? It's not the angle of inclination. Please make sure that you get that right, né?
Okay.
I'm not sure if you understand what I'm trying to say. Do you want me to repeat that?
Yes, please.
Remember, if we put let me show you what I'm trying to say. If I put something on an inclined like this, if I put something on an inclined, remember I'm going to have theta, and then I'm going to have a force applied. So I'm saying that this angle theta, that angle, it is not this angle. It is not the angle of inclination, but it's the angle between the force and the displacement. Do you understand? Are you happy with that?
Yes.
This makes sense, ne?
Yes.
Right. So we're going to do an example, ne? We're going to work on an example. Let's say we have a force like this, and this force is on an horizontal surface, and we have the force applied moving in that direction. So I'm gonna call this F applied, and let's say the F applied is given as 300 newtons. And let's say we have the frictional force going in that direction. We're going to call this FF, and let's say the frictional force is given as 120 newtons.
Okay.
So we need to know the direction of the motion. We're going to say that the direction of motion is going in that direction. Can you see my arrow? Where is my arrow pointing?
To the right.
Exactly. So now, this box is pulled across a floor by that 300 Newton force. So the force of friction is given as 120. We can see that. And is pulled a distance of 10 meters. So what we are saying is that it is pulled the distance of what? Of 10 meters. The distance is 10 meters.
Mm-hmm.
That's the path taken by the object. Okay?
Okay,
So now let's say we need to calculate. There are two formulas that we're going to use. I need you to know all these formulas. Ne?
Okay.
So now let's say we need to calculate the work done by applied force. So let's start using the formula work done by F delta X. That's the first method that you can use. Let's calculate the work done by applied force. What will be the work done by applied force using that formula? So if we use that formula to find the work done by applied force, this is what we're going to do. Remember already, we know what is the formula. The formula is WF delta X. So now we just have to substitute. Where there's F, what should we put? Applied force, which is 300, the displacement, which is 10. This is easy enough. Therefore, what is the work done? What do you get if you substitute that on the calculator? That should give you 3,000. Eh? Remember, this is in joules. Are you still with me on that?
Yes, sir.
100%. So now, let's calculate using that same formula. I want us to calculate this. I want us to calculate the work done by the frictional force.
Okay.
Right. So now remember, frictional force goes in an opposite direction, okay?
Mm.
If frictional force goes in an opposite direction, it's going to be negative. So the work done by friction, we're going to use the formula F delta X. But now what is the F? Negative 120. Remember, the frictional force is 120. It's given as 120, and it's moving in an opposite direction. So since it's moving in an opposite direction, we're going to say that the frictional force is negative 120 and times the displacement of 10. So the answer that you get, it should be negative 120 joules. But remember, the negative gives us the direction. So we're just going to say the work done is equals to 120 joules. So the negative gives us the direction where our work is, we are doing a negative work. So the negative tells us that the friction is doing a negative work on the object. Are you with me on that?
Okay. So it, like what we were speaking about, that it's not a scalar or a vector. Like it can still have a negative, but then you won't put any direction because work does not.
Oh, sorry. Remember that we said work is not a scale, it's not a vector. The negative tells us that this friction is doing a negative work. This negative tells us that friction is doing a negative work. I'm not sure if you are still with me on that.
Yes, I get you, so.
You get it, ne?
Yeah.
100%. So now, let's use the formula. Let's use the work done by F delta X, the cos of theta. Let's use that formula and see what we get. What do we get? If we use that formula, you just have to do the substitution first. Using that formula number 1, we need to calculate work done by applied force. So now what I'm trying to do is that I need to show you how to use this angle partner. So the work done will be equals to, what are we going to use? We're going to say this is FA delta X, the cos of theta. So remember, if we move up, what was the applied force? The applied force, 300 newtons. So I'm going to substitute this guy here as 300 multiplied by the displacement, which is 10. Now, what about the angle? What will be the angle? Remember, we said this angle is the angle between the force and the displacement. Now tell me, what is the angle between the F applied and our displacement? What is the angle equals to?
Isn't it gonna be? Is it the angle in between it? Isn't it gonna be 290?
No. The angle. Remember, this force is parallel to the applied force. It's parallel to the surface. The F applied is parallel. What is the angle? Do you see any angle there?
Oh.
It's like saying I have the F applied. This is my F applied. Then I have what? The floor. We don't have any angle, so the angle is 0.
Oh.
So always when you calculate the work done and the force is in the same direction as the motion, just know that your angle is going to be 0. So the angle will be 0. This will give us the cos of 0 degrees. What I'm trying to say is that I have F applied, then I have the motion, the direction of the motion. So since they are the same, the angle theta is 0. I'm not sure if this makes sense. Are you happy with that?
It makes sense.
Okay, great. Because it's very important for you to understand this, né?
Can the direction of motion be anything besides left and right?
We'll go too much. Don't worry, we'll do my example, né?
Okay.
Sure. So now what I'm going to do is that you punch that on the calculator. This should give us the same work that we got as 3,000 joules. So now I want us to calculate the work done by frictional force. So now let's calculate the work done by frictional force. What will be the work done by frictional force? We're going to use the same formula. We're going to say the work done by frictional force, that will be F delta X, the cos of theta. Please tell me if I'm moving fast. Remember we said that frictional force, one thing I need you to note is that when we use this formula, when we use that formula, we consider the direction of the applied force. So if frictional force is going in an opposite direction, we substituted that frictional force as what? As negative. But listen, when you use this formula, do not put frictional force as negative. Just put it as 120, but you're still going to get the same answer. I'm going to explain why. So now this will be 120. Our displacement is 10. Then the cos of, we need to understand the angle. Look at this. Look at this guy here. I'm going to have a frictional force. Look at this. I'm going to have a frictional force going. Okay, remember this is the direction of the motion. I'm going to write it here. This is the direction. And then we're going to have a frictional force going that side. So this will be my friction.
180.
Exactly. What will be the angle? Angles on a straight line. The angle will be 180. So now this tells me this will be the cos of what? The cos of 180. This should give us an answer of that negative answer, negative 1200 joules.
Yes.
Therefore, the answer will be the work done by frictional force is just 1200 joules. So now, the negative tells us that the frictional force is doing what? The frictional force is doing a negative work. You understand that part?
Yes, sir.
Are you happy?
Yeah.
So, remember we said work is not a scalar. Work is not a vector. So if work is positive, what happens? What can you say? What can we conclude from what we just discussed now?
That there is more positive work than negative work.
Okay. Okay. Maybe I can take that. We said work is not scalar.
Yes.
And then it's not a vector. So therefore we can conclude and say that if work is positive, what can we say about that? This tells us that if the work done is positive, we're going to say it means that energy is added to the system. So now, what if work is negative? So this tells us that if the work done is negative, is the opposite of that statement. I think this it's easy enough.
Yes.
And I don't think this is something that you can forget. So if work is negative means that this means
energy is added.
Energy is removed.
Oh, I thought so saying positive.
No. If work is equal to negative, the energy is removed from the system. This is good, ne?
Okay.
Are you happy with that?
Yes, sir.
Right. Listen.
Yo.
What's wrong? What's wrong?
What does that mean?
I just had yo. Is this too much?
No, it's not too much. It's not.
Let's talk about the network. Do you know what is the meaning of net in physics?
Total work.
Exactly, the total work. So now we're going to talk about the network on an object. The network on an object. Right. So when multiple forces act on an object, each force does work on the object to change its energy. I'm not sure. Let us not write that down. This, I think you get it now.
No, sir, please repeat.
Okay, maybe I should put it down there.
Yes.
I'm saying that when we have multiple forces that act on the object, this tells us that each force will do work. Or we can say does work on the object. To do what? To change its energy. I hope this makes sense. I hope you understand that, ne?
Okay.
Right. The net work done on object is the sum of the work done by each force acting on the object. So you're going to see this thing when we make examples. You're going to see this now. Just gonna start with an example now. Okay. Let's bring the object again. So this is my object. I'm going to have the work done. Let's say this is the work done by applied force. I'm not saying this is applied force. The work done by applied force. And this guy here will be the work done by frictional force. Let's say this is 25 joules. And let's say this is 65 joules. We have the work done by what? By applied force and the work done by frictional force. We are not talking about what is this? We are not talking about the force applied. This is not force applied. It's a work done. So let's say the direction of motion. So the direction of motion, it goes in that direction. Okay? So now let's first find the network. So a box is pulled horizontally on that floor, and the work done by applied force is given as 65, and the work done by friction is 25. They want you to calculate the net work done on the box. So in order for us to calculate the net work done on the box, you know what I'm going to do? We're going to say, first thing first, we need the net work first. W net is equals to, remember we need to choose direction. If we take right, that's not the spelling for right. If we take right as positive, let's just take, we take right as positive. So the net work is going to be the work done by applied force. We're going to subtract the work done by what? By frictional force. You understand?
Yes, sir.
So now let's see what will be the net work. So the net work will be equals to, we are given the net done by that applied force, which is 65. We need to subtract the 25. This will give us the net work as what? The net work as 40 joules.
Yes.
You understand? So that's the answer. So what I need you to understand is that the gravitational and the normal force do not do work on the system because they are perpendicular forces, no?
Yes.
So why the net work, why is normal force and Fg, the force of gravity, they don't do any work? It's because they are perpendicular to the direction of the displacement. Remember, this is the direction. The time I put normal force going up, you can see that normal force is perpendicular to that direction. So normal force is pointing up. So no work done. Same applies. Fg goes down, which is perpendicular. Fg goes down, perpendicular. No work done. Okay?
Yes, sir.
Right. So now let's add more. Let's make everything to start more interesting. Let's work on this one. Let's say we have an object like this. So on this object, we're going to have the F applied. So this will be my F applied, and let's say the F applied is given as 100 newtons. Right, or maybe we should just, okay, okay, you know what I'm gonna do? Let me move down. Okay, so I'm going to have a box here that is on the horizontal. Then we have the F applied. I'm going to say this is my F applied, which is 100 newtons, and it's applied at an angle, and the angle is given as 60 degrees. So now from this we have the direction of the motion. The direction of the motion is given, and we know that this goes to the right, so the direction goes in that direction. So now remember, we're going to have the F horizontal pointing in that side. We're going to have the Fy pointing up. This is my Fy, this is my Fx.
Yes.
And now they say that the frictional force move in that direction. You have a frictional force, so we're going to call this Ff. That's what we have. So it's Ff, and then from this we have the displacement that is given as 5 meters. You still with me?
Yes, sir. Yes, I'm still with you.
Okay. Let us calculate the following. Né? We're going to calculate let's calculate the net force. Let's start with the net force first, because you need to understand the net force before you can calculate the net force acting on the block. Remember, when we talk about the net force, we only focus on horizontal forces, because those are the forces that are doing work. So if I draw my free body diagram, I'm going to have my Fx going in that direction, and I'm going to have my frictional force F going in that direction. So the frictional force here is given as 20 newtons. The frictional force is given as 20 newtons. So what will be, we know that, if you still remember, Fx is equals to Fa, the cos of theta. So now, in order for us to calculate this, what will Fs be? Fx will be F applied, which is 100 newtons. We need to multiply that by the cos of 60 degrees. That's my Fx. And if I'm looking for F net, if we are looking for F net, say we take right as positive. So if we take right as positive, what I'm going to do is that I need to take my Fx, I need to minus what? My frictional force. And we set Fx, it's 100 the cos 60 degrees, we minus the frictional force, which was given as 20. The answer that you get is your F net. So the F net, what do you get on your calculator?
I get 30, sir.
You get 30.
Yes.
So this is F net. So it's going to have a magnitude and direction. So it's 30 newtons. Because it's positive, we took right as positive. Remember, this force, a force is a vector. So when you do your calculation, you need to be very careful. Because this force, your force is a vector. So since it's a vector, it has direction and what? It has direction and magnitude. You understand that?
Yes.
Yeah. The force is a vector and it will have direction. So now that we have the F net, the next question that they'll ask, they will need you to calculate the work done by that F net. They'll need you to calculate So remember, the formula that we're going to use is the work done by this. It's F net. You multiply that F net by displacement, then you are done. Because when you use the F net, we don't use the cos of theta net. So this will be the F net that you calculated, which is 30 newtons. You multiply this by that displacement of 5. That's how easy these questions are. And then you get, what do you get?
150.
150 joules. Thank you. Remember, when we calculate the F net, this F net here, we only include forces or components that act in the same or opposite direction of the motion. So there's only two forces that act in the same or opposite. Don't include more F applied, Fy. No, we need the forces that goes same direction as the motion or opposite direction as the motion. And I'm telling you, you'll be best, ne?
Okay, sir.
Don't include gravitational force. You don't have to include normal force or vertical components. These are perpendicular to the direction and they don't do any work on that box.
Okay.
Are you happy with that?
Yes, sir.
No, I think we're going to finish this topic today.
Let's push.
Yeah, I think we're going to finish this topic today. So this tells me that we're going to cover everything on this topic. Then on our next lesson, we'll work on past papers. I think we're finishing this today. Because look at this. Now we need to discuss what we call the non-consecutive forces. Do you know what is a non-consecutive force?
No.
This is what we're going to discuss. What we call the non-consecutive let me just remember the work done by a non-consecutive force is dependent on the path taken. You understand?
Okay.
Let's write it down. We are saying that the work done by a non-conservative force is dependent. It depends on the path taken. This will make sense now, ne? So what we are saying that in general, all forces you deal with that you did at school, ne? All the forces that you did at school and then all the forces that you did are non-consecutive force except for gravitational force. You understand? Applied force, frictional force, force of tension, those are non-consecutive force.
Okay, sir.
Applied, tension, and friction. You see these all forces, they are non-consecutive. I hope you understand that part, ne?
Yes, sir.
Okay, great. So now, non-consecutive force do not conserve mechanical energy. So we're just gonna put it down. These forces, you see these forces, they don't conserve mechanical energy. They don't conserve. Everything will make sense when we make calculations. They don't conserve mechanical energy. That's what I'm gonna give you for now. So now let's talk about consecutive forces and the work done by gravity. So because this one is very important, né? It's very important for you to understand what we call conservative forces, and we're going to also discuss the work done by what? By gravity. So if the total work done in a moving object from point A to point B is independent of the path taken, then the force is consecutive. Né? So what we are trying is that consecutive forces, this one, they depend on what? They depend, independent. Let's put it like this. Is independent of path taken. So if you see that the force doesn't matter about the path taken, just know that we call those forces consecutive forces. So I'm going to give you an example, and there's only one force that is consecutive force that you're going to do for now in grade 12, and that force, we call it the force of gravity. This is the only force that you're going to do that is a consecutive force. I'm not sure if you are with me on that.
Yes, sir.
So now, when we say gravitational force is consecutive, it's conservative force. What is that telling you is that the work done by gravity or against gravity to reach a point above the ground is going to be independent of the path taken. I'm going to explain this using, maybe we can just use pictures to explain this issue. Now, so what I'm saying is that if I have something on incline like this, and this is my point B, and let's call this point A, and we have a ball here. This ball, we need to drop it down. So this ball is point A, and we need to drop it down. I'm going to say this is my ball, and we need to drop it down. And then let's say that we create this thing to be on the same height, like this. The height like this, the height like this. Okay, and then let's have another guy this side, which is our ground. Then what we're going to do, let's say I have another ball that is on the same height. So this ball is going to move from this same height, and we're going to do what? We're going to drop it. It will move like that until it reaches the ground. And
Yes.
let's say that we have another one that we just gonna do it with free fall. Let's say this is my point A, this is my point B. We have another one here that we're going to leave it with free fall, and then it's going to drop to point B. So can you see all this thing, they go to the same level, which is point A. I mean, they move from the same level to the same point. So they move from A to B. You understand? 100%. So now, what I'm trying to say is that, remember we said that gravitational force is a conservative force. So the work done by gravity or against gravity to reach a point above the ground is going to be independent of the path taken to reach the point. What you are trying to say, if you can look at this three objects, in other words, look at this object. The work done by gravity on the ball moving from A to B is the same in all these three scenarios. I'm not sure if you understand what I'm saying.
Yes, I get it. They're all doing the same thing.
Yes, so what we are saying is that the work done, that is done by gravity, the work done by gravity on the ball from A to B, we are saying that is the same in all three it's very important for you to do that, because if you want to master if you want to really master those, if you really want to master the exam questions, you need to understand the concept first, okay?
Okay, so
Then you'll be able to do calculation. So now we're going to conclude. Therefore, for this one, remember we said non-consecutive forces, they do not conserve mechanical energy. So consecutive forces are the ones that the conservative forces, these guys, they are the ones that conserve mechanical energy. Can we work on examples now? Amisha, you still with me?
Yes, I'm still with you.
Okay. So what we're going to do, let us take we're going to say, we're going to do an example now. Right. On this example, we're going to say we have an object like this that is uninclined.
yes,
Right. So the object is uninclined. We know that this will be my theta. And then let's say that this object, we're going to name it as the object with mass m. Okay?
okay,
This object is going to slide down. It's the same object. I'm just going to put it like this so that you can see that the object, okay?
okay,
Let's name this point A. Let's name this point B. So now we can see that if this is A and this is B, this will be my what? This will be my displacement. Okay, maybe if we put it like that, but let's just say this is my displacement and we're going to call it delta x. Are you happy with that?
Yes, sir.
So there are some of the things we have what? We have a box that slides down a frictional slope. Né? When we say a frictional slope, this tells you that we don't have friction. Né?
Yes.
So this is frictionless. So I'm just going to write it down. Slope. The slope, we don't have any friction on that. So now, look at this. We have point A to point B is delta x. So we need to show that the question says, show that, let's show that the work done by gravity moving the work done by gravity moving the box from point A to B. The work done by gravity to move the box from point B is the same as the work gravity, and let's call this point C, and this will be the distance between A and C. We're going to call it h, the height. So we need to show that the work done by gravity to move the box from point A to B, it is the same as the work done by, the work done by gravity to move the box from A to B will be the same as the work done by gravity to move the box from A to C. You see, trust me, you're going to get this in an exam. It's always there in an exam. You just have to know what you need to do. So we're going to apply some of the most important concepts here. You will definitely get something like this in an exam. Trust me. You will definitely get something like this in an exam.
Okay, sir.
Sure. So now look at this. We are saying that we need, if this is the box here, this is my box. So if this is my box, remember, if something is on inclined, this guy here will have if the normal force acts up, we know that the FG perpendicular will go in an opposite direction. This will be my FG perpendicular. I'm not sure if you still remember that, Right. So if this is the FG perpendicular, we're going to have the force that always acts down. What is that force? Our FG. The gravitational force, you understand?
Yes, sir.
And now there's this force that always acts down. There's this force that's always acts down, and we call that force FG parallel. You know what I'm going to do? Instead of doing like that, I'm going to create a triangle. Look at where I'm going to put my FG parallel. My FG parallel will be like that. This is my FG parallel. So that we can create that 90 degrees. And according to physics, it was proven that this angle theta will be equal to that angle there. I'm not sure if this makes sense.
Yes, sir, it does. It does.
You get it, ne?
Yes.
Okay. So we are saying that this is what we have so far. So now, what I need us to do, first thing first, before we do any proofs, you still remember that I can say the sine of theta is equals to hypotenuse, not hypotenuse, it's opposite all over hypotenuse, right?
Yes.
Therefore,
Yes.
what is the sine of theta equals to? The sine of theta, my opposite is h. Can you see we are working with the big diagram? My opposite is h. So I'm just going to say this is h over hypotenuse. What is hypotenuse? Is delta x. Can you see that on the diagram? Remember, I have delta x moving in that direction like that, and I have my height moving in that direction. So my height is my opposite, and my delta x is my hypotenuse. Therefore, we need to make the height subject of the formula. Therefore, what is the height? Our height will be equal to delta x, the sine of theta.
Yes.
We're going to work this thing out. Ne? We're going to work this thing out step by step. So this is my height. So now what I need us to do, what we need to do is that we're going to calculate the work done by gravity from A to B. Let's work on it. So we're going to say we need the work done by gravity from A to B. This side we're going to need the work done by gravity. Again, we need to prove that by gravity from A to C. Let's start with the work done by that gravity from A to B. Remember the formula? We need the work done by gravity, which is equals to the force multiplied by delta x. So now, what is the force from A to B? Look at A to B. Which work is doing by when it moved to A to B? Which force is moving? The Fg parallel. You understand? So this side we're going to say the work done by gravity on A to B. It will be the force of Fg parallel, and then this should be multiplied by delta x. Are you happy with that?
Yes.
You good? Okay. So now I'm just gonna leave it like that. Let's go to A to C. We need the work done by this thing. So now if we are moving from A to C, look at this one. Which one is doing the work? The Fg, that Fg, I don't want to confuse you. Let's go back to that diagram there. Look at this one. The Fg is the one pointing downwards. Can you see that the Fg is the one that will do the work?
Yes.
Are you sure?
Isn't it?
Yes, it's the Fg. I'm saying that. Are you sure you understand?
Yes, I get it, sir.
Okay, so the Fg is the one that will point down. So now look at this. The work done by this will be F delta x. What is the force? The force we said it's Fg. Now what about the displacement? Can you see this one? It has the displacement of h. From A to C, what is the distance? It's h. So I'm going to say this is the displacement. We're going to multiply that by h.
Okay.
So you know what we're going to do next? We need to manipulate what? We need to manipulate this equation here. We already know what is h, nah? H is delta x sine theta. So I'm going to substitute this. H is delta x sine theta. So I'm just going to substitute this and say this is Fg times delta x. Oh, this is Fg times the displacement. This side it's h, and then this is the work done by the gravitation. So even if we start this side, let's say the weight it's equals to Fg times, we said this is delta x, the sine of theta. You understand? But now what is Fg? According to you, what is Fg? Remember that Fg we can write it as mg. So this can be mg times delta x times the sine of theta. So this is our work done by gravity from point A to C. This is the formula that you're going to use. You see now, if you understand how we got that formula, when they give it to you in an exam, you'll have the mass, you'll have the gravitational force, you substitute your displacement and the sine of theta. Simple. Let's move on the other side.
Sir, you
I'm sorry, I'm moving fast, ne?
you are that formula. Hi.
What's wrong with the formula?
Can you explain? So we just replace the h with the delta x sine of theta.
Yes, because we already know what is h. Remember from this?
Mm-mm.
You understand where is the h coming from?
Yeah, I get it now. Okay.
You understand, ne?
Yeah.
I have doubts. God, you don't get it.
I see it, you. And then we did the mg because fg is m times g. Okay.
Okay. So now look at this, ne? This side, we are looking for delta x. Okay? We are looking for delta x. Remember, when I have something like this, what can I do? I can say that where there's, we can just simply say let's go back here. There's something I need to explain here, because just because you asked me a question, maybe if I put it like this, nah? Look at this. Look at this equation. I can write that equation as, remember Fg, it's mg, nah? So I can say this is mgh. What is mgh? Is the change in potential energy. So it's EP.
EP, yeah.
Potential energy. You understand?
Yes.
Okay. Alright. So now we need to work on this, nah? We need to work on this other side.
Okay.
What we're going to do, you know what we're going to do? I'm going to say that if I have delta x like this, how can we introduce the sine of theta here?
Well, are we going to use that h is equal to delta x sine of theta and then manipulate it to get the sine of theta to be on its own?
We can definitely do that, nah? We can definitely do that. You know what I'm going to do? If I have FG parallel, remember what is FG parallel? Let's just substitute what we have. So I can say it's easy if we just look at this like this and say, you know what? We know that the weight done by gravity is equals to, what is Fg parallel equals to? Remember that Fg, if we put it like this, you know, that's why I like to use different markers so that you can see that this is separate information. So what I'm trying to say is that Fg parallel, we already know that is going to be Fg the sine of theta. You still remember that?
Yes.
And now what is Fg the sine of theta? We can write this as mg the sine theta. So look at this. Fg parallel is equals to that. Okay? So what I'm trying to say is that where there's Fg parallel, I'm going to substitute and say this is my mg, the sine theta times that delta x. So now can you see that we can arrange this and say the work done by gravitational force, so that it can be the same, is going to be mg, because it's a multiplication, the order doesn't matter, right? So we can say 2 times 3 the same as 3 times 2. So this will be times delta x times the sine of theta. So now we just proved that the work done by gravity from A to B is the same as the work done by gravity from A to C.
Yes.
Are you happy with that?
Yep.
Nice. And this is how we do this. So now, to conclude whatever that we were doing now, note this. What you need to understand is that, hey, I'm sorry, I'm moving like fast. Eh?
Also, I understand, so you can move. As
Okay.
long as I stop you when I don't understand.
So now what we can conclude is that the work done by gravity can always be expressed as the change in what? It can always be expressed as the change in potential energy. We're going to conclude and say the work done by gravity, we can always express it as the mgh.
Inch. Okay. Okay.
We're done with the non-consecutive forces. See, I told you, right? Faith and faith today.
Hey.
We are finishing this topic. If you see us doing power, then we're almost there. But if we don't manage to finish, even if we don't finish it, it's okay, ne?
Yeah, sir.
Yeah, I hope.
I'm so proud of us, though.
Or. Rapush again?
We are pushing, sir.
Yeah. Let's talk about the work energy theorem.
Theorem.
Yes. Yes, we do have the work energy theorem. That says that the work, and they'll state the work energy theorem in an exam.
Mm-hmm.
Consult your exam guideline. Eh? The
Okay.
work energy theorem, it states that the work done